So the next question is, what are the first two blue colors that show up? So if we imagine that this is the interference pattern here, violet at the top going through the rainbow and then showing up again, what two thicknesses would indicate a blue color? Well, here's our equation right here. And we know that the first two blue ones will be at n equals 0 and n equals 1. So if we solve this equation for the thickness, we know the thickness will be equal to, we'll just leave n in, n plus 1/2 times lambda. Now remember that the lambda inside the oil is going to be, lambda inside the oil is going to be lambda over 1.33. Because this refractive index has the effect of changing the wavelength. Recall that the refractive index is equal to the speed in the vacuum of the light in the vacuum divided by the speed of the light in the medium. Which is equal to the frequency times the wavelength. Frequency times the wavelength. The frequency doesn't change. That's coherent across the two interfaces, but the wavelength does change. And the wavelength here is just equal to lambda over the refractive index. Okay, so refractive index 1.33. Now I need some space to do this computation, so I'm going to clean this off and then get another screen. Okay, so we know that, let's see, T is equal to, I'm going to use the black again, T is equal to n plus 1/2 times lambda over 2 from this side. The criteria was 2t, 2 times the thickness. This is equal to the path difference. Delta path is equal to n plus 1/2 times lambda. Integer wavelengths of lambda. Integer and a half wavelengths of lambda because of the one reflection at the first, at the air oil. The first reflection is inverted. Okay, so we rearranged this and we have lambda over 2 times the refractive index. This is actually the wavelength in the medium in the oil, so we have to divide the lambda by the refractive index. So let's solve for the first two conditions. T equals 0 plus 1/2 lambda over 2 times 1.33. I know that 1.33 is the same thing as 4/3, so I'm going to just put that in here because Pete won't let me use a calculator. So we're going to put 4 divided by 3, put the 3 up there. So we have lambda over 2 times 4 times 3. This is the condition right here. This is the first thickness. Now I get to choose lambda because I don't remember exactly what color, what wavelength blue light is. And I'm going to make it a little bit easy on myself. I see that this is equal to 3 divided by 16 times lambda. So I know lambda is about 500 something. I can't exactly remember what blue is. And I could see if I pick 533 and multiply it by 3, I'm going to get 3 times 533 is equal to 1600. So I'm going to pick 3 times 533 nanometers divided by 16 is equal to 1600 over 16 is equal to 100 nanometers. That will be the first thickness at which I see the 533 nanometer wavelength light. I think that's roughly blue. Okay, now what's the next one? Well, the next one will occur when n equals, that was n equals 0, when n equals 1. So T equals 1 plus 1/2 times lambda over 2 times 1.33. And this equals 3/2 times lambda over 2. I'm going to do the same thing. I'm going to substitute 4/3 for this 1 1/3 equals, to get the same thing as before, except I have 3 times 3/16 times lambda. Same as before here. Now, again, lambda is 533 nanometers. I get, this is the same result as this one times 3. So the next thickness is 300 nanometers. That's the thickness. That's the second band. This is the first blue band, where I get the blue, showing when I'm viewing this, all this going on from this particular angle. So the first one is when the thickness is 100 nanometers. We get, we see at 100 nanometers, we see blue light coming at us when this is 100. And when it's 300 nanometers, we also see blue light.